Hello and welcome to this quick run through of today's lesson, this Friday the 8th of March, with me, Mr. McIver, for Further Maths Mechanics. This is a copy of the starter question. I'm just going to quickly jump past the solutions. This is an arrangement of a block lying on a table connected to a weight over a smooth pulley, and as you can see, the whole system is going to move round like this. It's the only way it can possibly move. So the first thing we do is we mark on the direction of motion and call that positive. So that's the positive direction, and by positive going to the right, I really mean round to the right and down. This is a one-dimensional problem, and the one dimension follows the line of the string. So once we've decided that, what we do is we look separately at the two particles involved. First, this one down here, the 4 kilogram weight. Well, it's obviously got a weight of 4g pulling it down, and a tension of T in the string, pulling it back up. Now, T is not going to be equal to 4g, because if it is, well, the whole thing is static and nothing moves. So I'm assuming T is going to be a bit less than 4g, so there's a net acceleration downwards. Now, the tension is the same throughout the string, so I suppose I can add another arrow there, T, and that's me done the block. Now, the block on the table of 5 kilograms, well, there's obviously weight acting downwards, 5g, normal reaction acting back upwards, also 5g because it's a horizontal table, and friction dragging it back against the direction of the motion. And using the equation we learned last time, we know that F equals mu r, where mu is the coefficient of friction and r is the normal reaction, and that works out as, well, 0.4 is the coefficient of friction, so 0.4 times 5g, the normal reaction, gives us a frictional force of 2g. We now set up a couple of equations, and this is where you have to think quite carefully. There is a shortcut for doing this, which, if you ask me in lessons, I'll go through with you. But this is the belt and braces way of doing this, which involves looking at the two particles separately. And what we do is we work out F equals ma equations for each particle separately. And if we do that, we get these two equations. First of all, looking at the block on the table, you can see we've got a force of T pulling it forwards, friction of 2g dragging it backwards, so the net force in that direction is T minus 2g, and the acceleration is simply ma, 5 kilograms times a. On the other hand, if we look at the weight hanging off the table, well, we've got a weight of 4g pulling it in the positive direction, but it's being held back by T, so the net force on this object here is 4g minus T. And of course, that's your F, so ma is simply 4a. Now you'll notice I've got a T in the first equation, a minus T in the second equation. So if I add those two equations together, I get 2g equals 9a. I rearrange my equation, and I can see I have a net acceleration of 2/9 g. It's greater than 0, so acceleration does take place. I've answered parts 2 and 3 at the same time. Now, there is a slightly more complicated situation where you have this kind of setup here. Here we've got an object in the middle of a table, a weight at this end, a weight at that end. You'll notice I've got the positive direction going to the right again. This is simply because common sense dictates that with 7 kilos at this end and at 2 kilos at that end, if it's going anywhere, it's moving that way. But now I've got three equations. Particle A, my forward force is this tension here, TA. My negative force is 2g, and the acceleration is mass, 2 kilograms times a. And so that gives us this equation here, TA minus 2g equals 2a. Looking at the one in the middle, I've got TC, this tension here, pulling it in this direction, TA, this tension here, holding it back. I've also got a force of friction here, holding it back. So altogether, I've got TC, pulling it forward, minus TA minus 2g, minus the frictional force, equaling acceleration. F equals ma. And finally, this one here, 7g pulling it forwards, minus TC, the tension in this rope here, holding it back. 7g minus tc equals 7a. I can combine my first two equations here to yield tc minus 4g equals 7a. And now I've got two equations in tension in C and 7a. I use those two equations to get an overall equation for the acceleration of the system, and then I can work through substituting and find all the different tensions and the acceleration of the system. The final example I want to look at is this one. We've got a block sitting on a slope inclined at some angle. Now, obviously the block might slide down the slope or it might not. First question is, given these figures, what are the critical values of theta for which the block would be at rest, and when does the tipping point happen? When does it suddenly start to slide? Well, here's our diagram, and this is a diagram you will be drawing an awful lot over the next 2 years. There's my block of mass m. The weight of it acting downwards is simply mg, but I need to split that into a component acting down the slope, which is mg sine theta. That's just GCSE trigonometry. Meanwhile, the component of the weight pulling it directly into the slope is mg cos theta. Now, the normal reaction is, by definition, perpendicular to the slope. And because it's not sinking through the slope, and it certainly isn't leaping up into the air, that normal reaction must be precisely equal to that force here pulling it into the slope. So I've got weight pulling it down the slope, a bit of the weight pulling it into the slope, and a frictional force, this frictional drag of mu r, tending to slow it down as it goes down. Now, I want to know the values of theta for which the block doesn't move. So in other words, I want my frictional force to be at least as big as the weight acting down the slope. So I want F to be greater than or equal to mg sine theta. F can be replaced with mu r, which can be replaced with 0.4 mg cos theta. And when I set out this equation like this, you can see the mg's disappear. I can rearrange my equation, do a bit of trigonometry, and come to the conclusion that as long as this angle here is less than 21.8 degrees, my block will stay on the slope. Finally, part 2 of this question. This question here is going to use a mixture of F equals ma stuff and Suvat equations. Here's how we do it. I have a similar set of equations, but instead of theta here, I've got 30 degrees. Now I've got mg acting down the way, so this is mg cos 30, and because I'm a maths teacher, I remember that cos 30 is root 3 over 2, so the component of the weight, which is pulling it directly into the slope, is therefore root 3 over 2 mg. Therefore, the normal reaction is also root 3 over 2 mg. The component of the weight pulling it down the slope is mg sine 30, and sine 30 is a half, so that's just mg over 2. The frictional force acting up the slope, mu r, is 0.4 times r, 0.4 times root 3 over 2 mg. I write down my net force equals mass times acceleration. Well, the net force down the slope is simply that minus that. So that's mg over 2 minus that yucky thing there equals mass times acceleration. This time all the masses cancel out. I do a wee bit of algebra and get a value for the acceleration. That's only approximate. I've rounded it off to 2 significant figures. And then finally, I substitute this figure here back into the appropriate Suvat equation. In this case, S equals ut plus a half at squared. It starts from rest. So I'm left with S equals a half at squared. I rearrange and I get a value of time for which it takes the block to slide 1.5 meters down the slope. These examples are in the book. By next week, I need you to have done all these questions here from exercise 3.1. I hope that makes sense. Email me if you have any problems.